Hello, everyone. Thank you for joining us this fine morning, almost afternoon. This is today's webinar, Machine Learning, a Pragmatic Approach to Adoption. And I'm your host, your MC, the Master of Ceremonies, Ned Bellavance. I am the Director of Cloud Solutions here at Anexinet. And before we get into the presentation proper, I want to drop a little knowledge on everyone about what Anexinet is all about. So Anexinet is a consulting company. We focus on 4 key areas. And if you want to scroll up there, sir. Thank you, Michael. So we focus on 4 key areas. The first is customer engagement. So that would be crafting and helping other clients craft engaging digital experiences for our customers. Making sure that they're having the best possible experience on that front end application. And we also focus on enterprise mobility, which to a certain degree lends itself to that customer engagement model. The enterprise mobility is more focused on internal consumers to your organization as opposed to external customers. How do we know we're doing a good job with all this customer engagement and enterprise mobility? Well, that's where analytics and insight comes into play. We need to analyze the data that we're getting from the customer experience and making sure that they're engaged and having a good experience on whatever device they are consuming. And then finally, what is all this stuff going to run on? And that's where cloud and hybrid IT comes in, and which is the group that I'm part of. We look at how can we most effectively run your workloads in the right place so that your customers and internal employees can have the best possible experience. So those are the 4 main pillars that Anexinet focuses on. But today's pillar is going to be all about analytics and insight. And to that end, now that we've gotten the appetizer out of the way, I want to get to the main entree with the run to my DMC, Mr. Michael Golub, Senior Vice President of Analytics and Machine Learning and a pretty good snooker player. Don't play him for money. Take it away, Michael.
Thank you, Ned. It is always a pleasure. Today, we're in for a fun ride, and the goal really to get through the main points of today is to have people understand what machine learning is versus AI, what constitutes a solid machine learning use case. Let's talk a little bit about the tools that are out there. What does a data scientist actually do? I hear that one a lot. And what are some ways to get started? So rather than make this an academic exercise, we're actually going to use some examples. I feel like an example is worth 1,000 explanations. And what we're going to do is go through an example where we're using adverse event detection with multiple classifiers, of course. And we're doing so for a business purpose. What we're going to do today is take as our centerpiece an example of a solution that really needed to be solved in the real world. And we're going to talk about how we can use algorithms to approach these problems. But more than that, we're going to keep relating the pieces of machine learning that you're hearing about back to business needs. This is not a machine learning 101 course right now. Even though we're going to be using code, this is not going to be an explanation around the math behind the algorithms, though if anybody wants to chat afterwards, that's one of my favorite topics. What we're going to do today is really bring this to life and give everybody a sense of where to get started, why, and how. So for an example, to get us through as sort of our centerpiece, we're going to be talking about the way that customers right now can influence sales directly and indirectly. And by this, what we mean is that you don't simply have to cease to buy from a brand in order to negatively affect it. These days with social media, a carefully placed tweet or a blog can considerably damage an image that's been carefully crafted for years by a company. We've seen this happen a lot, and this doesn't even take into account some of the things that can be done today to create fake impressions. Just a natural, honest to goodness negative review multiplied by 1,000 times can really do some damage to your business. So what we'd like to do today is talk about adverse event detection. It's a fancy way of saying finding out when bad things have happened. And we're going to use for our industry example, the pharma industry. In pharma, one has to be very careful about the safety of the drug and equally careful about the perception of the safety of the drug. So as we go through our example today, we're going to talk about creating a solution that allows a pharma company to look at social media and figure out who's saying what about the company in ways that could be potentially damaging. In pharma, there's a thing called an adverse event, and that's when something adverse has occurred as the result of a drug or a claim that something of that nature has happened. And what we'd like to do in our example is set up a machine learning solution that can scour social media and find tweets or texts that indicate an adverse event has happened. Why do we want to do this? Because rather than pay hundreds of analysts to sift through tens of thousands of tweets, we'd like to automate the process and then have a few expert analysts follow up on those potential adverse events and figure out what needs to be done in order to rectify the situation. So before we go too much deeper into it, I'll just give you a personal reflection on how I find a particular platform and how it's been working for the experimentation that we do here at Anexinet. 6 months ago, it took me days to get set up what I can now do in SageMaker in minutes. And I'm going to be using SageMaker today to show you some examples of machine learning and data science experimentation in action. And the reason I was able to do this so fluidly is because all the libraries that I need were already installed. By the way, anything that isn't installed, I don't have to break out of SageMaker in order to install it. Anything that I do install remains in my notebook, and I'm free to develop my own models. So you might be thinking, SageMaker, models, all this sounds a little bit foreign. We're going to hit the glossary right after I talk about our approach a little bit, and then hopefully make clear what you're looking at right now, why you're looking at it, and give a little bit more context to this journey that we're going to go on over the next 40 minutes. So our approach, as we had talked about earlier, is to solve a problem where we're concerned about statements being made about our company or our product. If we want to make a machine learning solution, we have to fully define our problem. Saying things like, I need to figure out which tweets are bad is a good start, but we need to state our problem in a way that could then be solved through an algorithm, and we'll walk through how you do that. And then we're going to build a solution. In order to build a solution, we have to find data, we have to load it, we have to assess it, we have to evaluate algorithms, and we have to train a model. We have to test our model, we have to tune it and deploy it. That, by the way, is the exact set of steps that you go through when you're using SageMaker on Amazon Web Services. You go through a build process, a train process, a tune process, and a deploy process, and we'll touch on all of those as we go. So without further ado, let's get started on our own machine learning project. As I had promised earlier, we're going to do a glossary. This glossary is not official. I wouldn't take this and necessarily use this to define the entire industry, but these are words that come up very often when we talk about data science. Some of this you'll find similar to definitions on Wikipedia. Some of this is just simplified language so that the rest of this talk makes a little bit more sense in context. So from a business perspective, we want to understand the following words so that we can talk about doing a machine learning project. A lot of people say, what is artificial intelligence? I don't mean to be a smarty when I say it's intelligence demonstrated by machines. The reason I use a very broad term for that is because there are many things today that are examples of artificial intelligence, and there are many others masquerading as examples of artificial intelligence. I believe somewhere that there, no joke, I think that there's a toothpaste that has claimed to have artificial intelligence built in. So there's a tremendous hype cycle. And when we talk about artificial intelligence, it's important to bear in mind that the technology we're discussing or the concepts we're discussing go back to the 50s. So rather than quibble about what things are AI and what aren't, rather let's talk about machine learning, because that's a very practical subset of artificial intelligence where we use statistical techniques to give computer systems the ability to progressively improve performance on a task. And we use data rather than programming in rules in order to do it. So by joining this seminar, you probably already know a little bit about machine learning, or maybe a lot. You're already using it or you're about to. The thing that I'd like us all to agree on is machine learning is just one subset of artificial intelligence, and it's meant to specifically solve individual problems. It's not generalized intelligence. Machine learning doesn't claim to ever be able to have autonomy or to be self-actualized. It is a process that we put to work for us, and we do it using data science, which is the art of working with data and algorithms to create models. And a model is the result of doing this work. It's the thing that you use when you make predictions in production. I'm going to skip over classifiers for a minute because, again, I'm using another word that's new, predictions. And prediction is the output of a model for a particular example. So if you're trying to see if a tumor is malignant or benign, you're making a prediction. And we're used to using the word prediction to mean guessing what's going to happen in the future. In machine learning, we use it to indicate that the machine has properly made a guess at an outcome. Maybe you want to determine what would be the average price of this house based on its location and square footage. That would be called a prediction. A classifier is a model that sorts things into categories like cat, dog, person. A training set is the set of data you feed a model. A test set is how you determine whether or not it works. And a matrix, it's a math construct that we use for data manipulation. I know that's a lot of words. You already use most of them in some form in your language, like the word set or training or learning or model, maybe not algorithm so much, and matrix, but these are the words that comprise the heart of machine learning from a business perspective. We have to, at the very least, understand from a business perspective, what are we trying to do? Are we trying to classify something? Do we have a set that we can use to train it? These are the table stakes in order to get a machine learning project off the ground. So having gone through a little glossary, let's talk about doing the build portion. And we'll start with defining our problem a little better, and we'll get a feel for our data. So next up, we're going to do some more problem definition. Then we're going to load some data in. We're going to assess it. And we're going to evaluate some algorithms. And I'll explain further what it really means to load in your data, what it means to assess it, and what it means to evaluate it. Understand that from a business perspective, if you are, for example, rather than pharma, you're thinking from the world of finance, and you're concerned about trying to predict fraud based on some indicators or extend a loan based on some key elements about a particular client. Defining your problem carefully and knowing how much data you have available is going to be the either green or red light to the beginning of your machine learning project, which is why I talk about these things up front. If you can't properly discuss the problem you're trying to solve, and you can't get your hands on enough representative data or buy it, and in some cases you can even synthesize data, without these two, you're not able to get to the point where you can evaluate algorithms. A large amount of time is spent upfront recasting problems in ways that could be put to use in a machine learning way, and then loading in data and taking a look at it. So what's our problem? Ned, what's our problem?
What's your problem?
That's what I'm thinking, right? So our problem is we need to continuously monitor tweets to identify the ones that need to be addressed most urgently. Here's what we know. There are thousands of tweets we need to review every day. Some of these might represent an issue that we need to address. We don't have time to read and think about each one. And luckily for us, we have a large representative set of tweets that have been categorized by hand. Another word for that is labeled. So if you have a set of data, it's labeled when you've taken the time, and usually this is done by humans, when you've taken the time to look at each element of the data set and categorize it. Now you might be saying, well, if I was going to do that, why am I paying to have a machine learning solution? I can just have people label my data. The idea is to take a representative data set and label it so that then you can teach the machine how to keep guessing properly when it's in production. So if we've got some data and we're able to talk about our problem in a way where we can frame it up in a machine learning context, we've got to take some time and dive in and take a good look at our data before we can choose models and do training and tuning and all that good stuff. So let's assess our data. Let's get a feel for it. Before you start running any machine learning algorithms, you want to take a look at your data and do some basics. Figure out whether or not you believe you can, using data, support the claim that you're making about a prediction. So For example, if we've got data and we're classifying it into adverse events and non-adverse events, tweets that don't have a problem and tweets that do, we want to do a little bit of upfront visualization so that we ourselves get a feel for what's that representation look like? What's the current distribution of data? So in machine learning, what we do as data scientists is we import some helpful libraries. And right now we're using a whole series. I'm not going to fully explain these. You can see them on screen, and some of which are actually being used for us to more easily work with Amazon's S3, where we're actually holding some structured and unstructured data. And we're loading up some libraries. I'm just including a little NASCAR here as a shout out to the libraries that we all love so well, Pandas and NumPy and Matplotlib. And those libraries come installed on AWS. So we can use those directly, but let's just say that we wanted to add a couple of libraries that aren't native. So I want to install word cloud because later on in this discussion, we're going to do a little word cloud and show which drugs pop up in it. I can just install them right now, right from the notebook. And Jupyter Notebook is what we're looking at right now. It looks like a web page, but it's actually an integrated development environment for data science with Python as a backend. So I just installed some additional libraries that I needed. Now they had already been there, which is why it says satisfied, but it's as easy as that. Right from the notebook, you can install additional libraries as you need. So we're going to specify an S3 bucket. It's a path to our artifacts. And if I click right here, we can just bring that up and you'll see that we've got our AE detection files. And those are just comma separated value files. And let's just pop back to the main discussion here. And when we've loaded up the data from our bucket, we're then going to put it into a matrix. You know, Ned, what the common question is about the matrix.
Are we in it?
Yes, and what is the matrix? And we're about to answer that just now. So what is the matrix? A matrix, for the sake of simplicity, is a mathematical construct and also a computer construct that we use to hold numerical values. And a two-dimensional matrix would look like a traditional grid that we would envision with an X and Y axis. We have multi-dimensional matrices that can't really be drawn in an easy fashion. And those are used for us to train machine learning models to make predictions. So we're just going to load up a few matrices now, and you can think of them for the rest of the talk as holders of information. And we've declared these matrices. We have 4 of them: training features, training labels, test features, test labels. So if we're going back to pharma, and let's say in this case we're talking a little bit more clinically, let's start using some of the words that are used in data science. And I don't mean to educate on words that you have to know in order to be a data science technician. These are words that you're going to need to understand as a consumer of machine learning at the C-suite level, at the director and manager and PM level. These are words that are going to come up. These are really important. So I'm not throwing this around to try to make data scientists out of everybody. We all need to be able to discuss features and labels. That's the heart of the matter. And to use it in context, if we were to take a look at this graph, you see that we have some categories, age and tumor size. So if by looking at a person's age and the size of a tumor, we could determine whether or not it is benign or malignant, that would be a great machine learning algorithm. So what we would do is feed the algorithm pictures of tumors, and they would be labeled. This is benign, this is malignant. By using the data that's supplied, we're able to train a machine learning algorithm to create a decision boundary. That's that little line that's going through there. And we would then, by feeding it new data, we could rely on the machine learning algorithm to take that new data and properly sort or categorize that element that we fed it into one of those 2 labels. So just to wrap it up, you have a tumor in this case, which is an element or an example. And an example can have features like the age of the person that the tumor is in and the size of it. The labels are applied in order to teach the machine learning algorithm, benign and malignant. Thank you, everybody, for sitting through that. That is all the math we're going to do today. Now that we've talked about those words, what we're going to do is we're going to load in a data set. And we're loading it into a handy little package called Pandas, which is fantastic for slicing and dicing data. And it's time for some data science. So, just like that, we are now going to do some of the things that data scientists do. Now, up front, you're thinking to yourself, this is really going to be dry. And I promise you, we will fly through this piece. But when you see what goes on in a data scientist's mind, it'll also help you determine, do I need data scientists? Do I need to start a data science team? How am I going to get this project off the ground? There's a necessary trait that most data scientists have, which is their ability to look at data sets and start to deduce patterns through using visualization. Right now, what we're doing is we're looking at a set of tweets. As we mentioned earlier in our example, we want to figure out which tweets, when they come in during the day, are ones that could be an adverse event. So we have a labeled data set here. Those things that are labeled with a 1 are tagged as adverse events. So if we look, for example, and you'll see the word drug in capital letters, that's because we had to do some redaction, and in this data set, remove any direct references to the drugs themselves and replace them with the word drug. However, it doesn't negatively affect the algorithm at all. So we have a set of tweets here, and some of them have been hand labeled as adverse events, where you see a 1. The ones that are non-adverse events are labeled with a 0. I'm not expecting everybody to read this very quickly as I go, but just to get a sense that we've got a pretty rich data set that we now can use to train a machine learning algorithm. So let's take a look at our test set. These are just the first 10 rows. And remember, as we said earlier, you need a training set and a test set. The training set is the rich data you use to train an algorithm, and the test set is the data you use to make sure that it's doing its job and you see how accurate it is. So our training set has roughly 9,000 elements in it, examples, and our test set has about 2,000. And that's just fine. You can talk about industry standards where a certain percentage of your full set of data needs to be separated into training and test. So let's get a little bit more intuition about our data set. And we're using Seaborn, which is a nice graphical package to show us in our set. You can just eyeball it and you can see that there are more non-adverse events than adverse events in our training set, and you would hope to see a similar distribution in test, and we do. So next would be getting an intuition about the content. Let's generate a word cloud. And the way word clouds work, and the way this one is set up at least, is the relative size of the word corresponds to the relative frequency of that word in the data set. This is a nice way to just get a feel for what's going on in your data set without trying to apprehend a gigantic histogram or bar chart with thousands of words, starting from the most used to the least. Obviously, the word drug pops up quite a lot. We see words like feel, day, still, time, started, treatment, pain, skin, migraine, med, feeling, chemo. So these are the words that are being used in our set. This helps us to get a sense of the prevalence of some of these words, and it makes complete sense for a set of tweets that are referencing pharma. So we're going to now copy our data into matrices. And again, to try to tie this back to business, let's say we're talking about retail and we're trying to predict customer churn. You would have to, in that case, do the same work. Now, rather than looking at words and tweets, what you would do is follow patterns of, say, subscription or purchasing patterns. You would still have to load that same data into a set of matrices that you would use to train an algorithm to try to predict whether or not a person or a group of people, based on some of the input that you were able to collect, are going to discontinue to be your clients. So again, this applies across every industry, and you would use obviously different algorithms, but you can't get away from first setting up your data. So we're going to import some additional data science libraries. Again, you can kind of read it on screen. I'm not going to go through exactly what each one is. Today we're doing a bring your own model, and I'll talk a bit more about that later. Bring your own is a fantastic feature of SageMaker where you can use SageMaker's highly optimized models. We'll talk about those at the end. There's a dozen models that have been specifically optimized for the platform. However, you're not relegated to using only what's in the box, quote unquote. You can design and develop your own algorithm. I happen to be using a couple from scikit-learn, a very popular set of data science libraries. There's a little video that I typically show. I'm not going to show right now because it's not going to come over all that well across our webinar. However, as we do our follow-up, we will send some links out to it. It's very motivational, having to do with some work going on right now on the AWS platform with a company called Skin Vision that's able to use mobile technology to help you classify whether or not a mole on your skin may or may not be cancerous. So we've taken some time to understand our data. I will, again, send you all the link to the motivational video. Now we have to choose an algorithm. We've got to train a model, and we're going to test and tune it. So I lied earlier when I said there would be no more math. There is math, however, I'm not going to talk about it. So you can just look at it and cringe. We're not going to go very deep into it. But what we're going to do in this case is we're going to use a thing known as a multinomial naive Bayes classifier. You can just take my word for it at this moment that this happens to be a very handy algorithm when it comes to dealing with words, particularly when you don't care about word order. And a question that often comes up is, well, how'd you know that? And this is something that can be answered in a lot of ways. Why would we use this? How did I know that? How does anybody know that? There's a body of ongoing research, and there's a community that shares in a quite lively fashion across many platforms, such as GitHub and Kaggle and other areas, that makes it very repeatable to choose an algorithm and to see how it does. So the scientific community has gone quite a long way in helping us figure out which algorithms tend to work well in which cases. It's not a complete science right now. I'll say there's an artistic component, but there are mappings that can be done. And when you align yourself with a company such as our own, we have experience that will help get us geared towards the proper algorithm, perhaps sooner than needle in a haystack mentality and even some of the more automated applications out there that tend to just spin through every algorithm until they find one that works. So looking at this classifier, we're going to skip over the multi-layer perceptron for the moment and do some things to our words. We're going to stem them, which means just taking off the ending, so it'll turn the word hurting into hurt. We're going to tokenize them, basically get them ready to go into a matrix. We're going to set up a little pipeline. And this pipeline does a whole series of things. It's going to call up our classifier. It's going to do some transforms. It'll tokenize. Again, we don't have to get too deep into it today. But why am I even showing you this? Because when you're solving a problem for your particular company, whether it's a problem about call center or logistics or conversion or trying to forecast sales, these are the very same things you're going to need to do. You'll have to have a pipeline that's able to be called up in order to take your data and to sort it and to tokenize it and to vectorize it and to get it into matrices. There's no way around that, regardless of what algorithm you're using or what problem you're trying to solve. So let's train the model using an algorithm. Let's test the model, and let's tune and deploy it. So today, we're not going to go too deep into deployment. I have a deployment that I run off to the side, and I'll get that started now. But what I really want to focus on more than anything else is just tuning. So let's just fire off our little model deployment over here. And we'll start that running. And pick up where we were. And getting back into now what? Sorry, everybody, for jumping around that way. Don't mean to give anybody vertigo. So let's train our model. Now, this is the moment of truth. We've taken our data set. We've taken thousands and thousands of tweets, and we're going to now, using a multinomial naive Bayes classifier, train a model to make predictions on whether or not something is an adverse event or not. So the work that we've done so far has all been around data. We haven't written a single rule. And it took 8 seconds of wall time. Wall time just means if you were to start a clock on the wall, how long would this algorithm take in real time? So in 8 seconds, we've taken those thousands of pieces of data, and we've trained up a model in order to determine whether or not any given tweet is an adverse event or not. So let's run our model, make some predictions, and then take our test set So we had about 9,000 training examples, and we've got about 2,000 tests. What we're going to do now is we're going to take that model and we're going to throw 2,000 test subjects at it. We're not telling it whether it was an adverse event or not. We're going to ask the model to guess, and let's see how it did. It got an 83.9. Well, that is something that you can expect when you're using the right model for the right problem. Right off the bat, we're getting close to 84% accuracy. No rules, no coding, just simply training an algorithm using your data set. And you say to yourself, that's good, but how does it compare to human quality scoring? And depending upon the type of problem you're solving, if we go back to retail, how good right now are humans at guessing whether or not a certain segment of your market should be getting more ads put their way or not? So many times we don't even have the answer to what human level performance is. In the case of tweets, we could measure human level performance and throw the test at a bunch of people and see how the model does. But it's important to understand that looking just at scores isn't the only way to determine whether or not an algorithm is good for your usage. So let's take a look at what that percentage means in real terms. And by that I mean, how does the model do when it's guessing whether or not something is an AE or not? And how does it get it right and how does it get it wrong? So to do that, we've got a little graphic here. And unfortunately, and this is where I'm going to be really apologetic about the data science community, they call the name of this a confusion matrix. I feel that's almost unnecessary. It's already confusing enough. But yes, we have a thing called a confusion matrix. Why is it called that? Because it tells you where your model confused one thing for another. So the way to read this chart is this. When we throw an adverse event at our model, it predicts an adverse event about 1,300 times. When we throw an adverse event at our model, it predicts a non-adverse event 140 times. Said differently, it gets it right. It knows that an adverse event is an adverse event about 1,300 times, and it gets it wrong about 140 times. But there's another side of the coin. When we throw at a non-adverse event, 620 times, it calls it. It knows it's not an adverse event. 240 times, it gets it wrong. And that non-adverse event is called an adverse event. So let's talk about that for a minute. Based on the problem you're trying to solve, sometimes getting complete accuracy all the way through is more important than just simply making sure that your false positives or false negatives are in check. And by this, I mean, in the case of a pharma company looking to be sensitive to potential adverse events being reported, if we had a model that was pretty good at getting it right when something was an adverse event, but it wasn't so good at guessing when it's not, then what would happen? We wouldn't be missing the opportunity to take care of bad tweets, but we might be looking at more tweets than we need to. That's an acceptable mistake in that situation. But there are other situations where you would incur much more needless cost or even have bad results if you weren't very careful to make sure that the negative case was taken care of properly as well. So when you're talking about predicting population movements, when you're talking about trying to determine coverage from a marketing perspective, you would need to be equally concerned with getting things that are labeled a certain way, labeled yes when they are and no when they're not. So let's take another look at AWS from a separate perspective here. And we're going to look at a Precanned model. And by that, what I'm doing is using Amazon's Comprehend. So you saw us use our own. You may remember I used the word multinomial naive Bayes. We used a model that we imported. Well, we used an algorithm we imported. So now what we'll do is use a Precanned model, and it is a sentiment analysis model. So if I say this is a problem that I see here, we don't even need that. And if we take a look, this is just raw JSON coming back. You'll see that it comes back and it's saying it's negative at about 84%. And there are 4 scores always. A thing can be negative, mixed, neutral, or positive. you notice it's very strongly skewed towards the negative. If we were to run this again and say, and these are easy, I'm just throwing it softballs here. You'll see now, obviously, that it's very much skewed to the positive. Models like this have been optimized by Amazon so that you can take in virtually anything and pop it in. And there we just gave it a sentence having to do with an explanation. And you'll see this comes up strongly neutral because it's a pretty neutral sentence. It's just a fact. I throw that in there to give everybody a sense of what's going on behind the scenes with the pre-canned models. These have been optimized. And not only that, but there's APIs around them that make it so that if you're designing a machine learning solution that needs to embed with another existing part of your product, they're able to do so with a pretty low code, no code way about it. So we've taken a look at models, we've looked at algorithms, we've talked a little bit about different industries. One of the things that we like to do is go through these same things in more depth at Anexinet when we do a machine learning kickstart. And that is something that I'll talk about a little bit as we kind of move to our conclusion, and then we can get to some questions and answers if that's okay, Ned. In order to take this to the next level and to really figure out whether you've got a good machine learning problem on your hands or whether or not you need to hire an army of data scientists, or what would be the best path to starting to use this new and exciting technology in your organization, we would want to talk more about industry approaches, things that have worked for various industries, anomaly detection for manufacturing. And then we would want to get into talking about how to use best of breed solutions. So if any of these problems ring true for you, such as I need to know how my customers feel, I need to forecast sales over time, what's my projected click-through rate, who am I looking at, where should I target my ads, should I extend credit to this person, I need to group these emails and tweets by topic, I need to monitor and analyze video, I need to translate speech to text. Every single one of those has a model that has already been optimized by AWS and is resident in SageMaker to be used. It's a pretty advanced thing that Amazon has done here, insofar as they haven't just round up models and given access to them. They've optimized them for their specific architecture. So these models will run in a fraction of the time of a similar, what I'll call generic model. So you could find examples of these very same models that have not been optimized, and you'd be looking at them taking much longer, and they would probably be much more difficult to tune. There's hyperparameter tuning that Amazon has also automated for you. And this style of mapping these questions to these algorithms is something that Anexinet specializes in. And that's kind of what we wanted to give you a sense of today, is that you're not alone. And if you want to talk about this further, we can engage in a kickstart, which is essentially a version of what we're doing now, but specifically geared around your set of use cases. And we're able to get in and talk very deeply about your business drivers, your market opportunities, your use cases. We can do risk analysis, design a portfolio for you, go through readiness, do recommendations and action plans. And at the end of it, you would have direction setting, you'd have your assessment. We would be able to capture ideation and concept generalizations, prioritize roadmaps. One of the things that's very popular is the machine learning project portfolio. When we put that together, we're able to give you a matrix that shows the best areas for you to focus on based on the level of data and the problem definition that you have. And then an executive readout that talks to you about your resource needs, your planning timelines, and next steps. So with that, Ned, I'm wondering if maybe we go through some questions and comments that might have come along. And again, for everybody out there in TV land, thank you for letting me prattle on without taking pauses for questions. It's a lot of material to get through, but let's maybe open it up a little bit now.
Great, thank you, Michael. So I think the first question that came in, and if I could just sort of adjust a little bit, is that they were asking if the deck is going to be shared. And I understand that this is not a deck. So I believe you said it up front, but in case anybody missed that, you were using a Jupyter notebook for this
Yes.
presentation.
Yes.
Can you talk a little bit about what a Jupyter notebook is and why it's ideal for this type of workflow?
Sure. So a Jupyter notebook is a construct that appears like a web page, kind of like it does right now. And if I kind of go back into normal browser mode, this is a web page like any other in my browser. However, behind the scenes, it's a fully decked out Python-based integrated development environment that has access to all the libraries that are running on whatever server you're on. So in this case, I'm running on SageMaker, which is underneath it all an EC2 instance. And Jupyter has become really popular in data science because it allows you to do things like we're doing today. You can put together very, very rich, self-explaining applications. And this Jupyter notebook that we're looking at now is the type of thing you see when you go into the research community and you're looking at a new algorithm. If it's well documented, there's annotations and pictures around the data. While the code blocks that we went through, these pieces right here, are the things that actually run. It's the explanations around it that are oftentimes more valuable when you're trying to come to conclusions. That's also something that our partners are left with when we conclude a machine learning kickstart, is a version of a Jupyter notebook that was used to do some initial modeling and kind of helps keep them going. So yeah, Jupyter notebook at the end of the day looks and smells like HTML, but it's actually a full Python environment.
That's pretty cool.
Yeah.
Another question that's come up is, I think I might have a good use case for machine learning, but how can I tell?
That's a great one. We get that all the time. It's generally not so binary. This is or this is not a good machine learning problem. However, what we like to do is sit down and talk about, is this a problem that you're solving today? Are you solving it routinely? How many people does it take to solve it? Is there a specialization in knowledge in order to solve it? What data is being used? Is it being done heuristically? Are people just guessing? Is it something that only the person who's really good at it can make predictions on? The more we know about the way that you're currently going about it, the better able we are to recommend either going down a machine learning path or not. I will also tell you that at Anexinet, we believe one of our mantras is no data science hammers. Very often, people see a nail everywhere and believe that machine learning should be used, and there are cases where you can solve a problem much simpler just using some very basic statistics or even a well-tuned SQL query. So machine learning is not necessary for every endeavor. Getting through to which ones are good and bad also has a bit to do with the quality of the data and whether going forward you would still have access to rich data that you could use to make your predictions.
Great, thank you. Another question that came up had to do, and if I could just sort of rework it a little bit, you had showed some of the Precanned models.
Yes.
And some of the custom models.
Yes.
How do you decide whether to build your own model or use one of the Precanned ones?
That's a great one. So we typically will opt for models that have been optimized whenever we can, for reasons which are obvious. Somebody has already gone through the time and trouble to set them up and to put the hyperparameters in place and allow us to do all the optimization. However, there may be a case where the approach that is going to be best for this solution is either a combination of canned models or a proprietary model or a model that needs to be optimized in a way that's different than perhaps how AWS foresaw it being used in a general case.
Okay, great. That's a really good one. Let's see if there's anything else that comes in. I'm curious about this. How can I tell which algorithm is the right one to use?
Yes, so this I think is akin to, and I'm not a golfer, but when you choose, which iron to use, a lot of times people say you just know. So I'm not a big fan of you just know when it comes to algorithms. However, when you've been around the different algorithms for a while and you've seen which ones have been used successfully in problems that are close to the one you're doing, then you have a good starting place. So there's more than enough information available on the web right now talking about use cases for individual algorithms. What's difficult, I think, for a lot of people is figuring out whether or not it's been repeated enough that it's reliable. So at Anexinet, one of the things that we do, and why you see this list, which is something we put together, we associate blazing text with customer sentiment. We associate, DBAR with sales forecast. These models that are already optimized may or may not be advertised by Amazon or anyone else for these specific problems that we have listed here. But we over time have come to see that they are applicable to these problems, just having worked in that space. The other thing that's a good idea to do when you're trying to assess a specific algorithm is, like I had mentioned earlier, take a look and see if others with a similar problem to you have used it successfully. And a similar problem to you might not initially seem like the same problem. You might be saying, I'm trying to predict sales, and somebody else may be trying to predict, periodicity of wildfires, but the two of them have a time series component and seasonality to them. So sometimes it's really important to be able to step back and figure out, what is it about the way I'm trying to solve this problem that would require machine learning? Another problem might require machine learning the same way. Let's look at that algorithm.
All right, good stuff. I think we got time for one more. I'm going to pick this one. How can I tell when I need to start a data science team or start hiring data scientists?
All right, another question we see a lot. So I would say the best time to hire a data scientist is after you've got something for them to do. And I know that sounds a little persnickety, but we've seen some folks get involved in building out data science teams. And I had said earlier, where there's a hammer, there's a nail. Sometimes you can have a rebel without a cause mentality. If you haven't gone through the process that we did, higher up on our screen earlier today, where you're able to describe your problem, you have data, you've got some of it labeled. If you don't have that stuff in place, you might be a little premature bringing in a data scientist. Data scientists come in many flavors. There are some that are more generalist. There are some that have specialization. Somebody might come in and say, I'm a natural language person, or I'm a vision person. The vision data scientist is going to know all about convolutional neural networks, right? Depending upon the problem that you have, going out and grabbing a data scientist may or may not be the best idea. And I would say there's a couple of table stakes you need. You need your problem defined. You need an already labeled data set, especially if you're doing supervised learning. Supervised is where we give labels, unsupervised is where we don't. But if you hire a data scientist and you expect them to hand label data, you're going to have an unhappy data scientist. So yeah, have your data in order, have your requirements in order, and I would say only then dip a toe in those waters.
All right, great. Thank you so much, Michael. I think that's all the time we have for today. So again, thank you everyone for joining today. Very much appreciated, and we hope that you have an excellent remainder of the day.
If I could just put out one little call to action. If some of this is interesting and you want to know more, we are going to follow up, and a Kickstart is a 1 or 2 week process, which is a great way to explore this further. And the questions that came in, those are exactly the questions that we answer. When you're done the Kickstart, you'll know if you have a live one on your hands, you'll know if you need a team of data scientists, and you'll actually have a starting point with an example model already trained, pointing you in the right direction. So thank you everybody for listening. Ned, thank you so much for hosting and helping me out here.
Anytime, sir. Take care, everyone.